Assalamu alaikum. Welcome to lecture 4 of chapter 6. Chapter 6 is of course mechanical properties of metals. Today, as usual, we will first review quickly what we did in lecture 3. Then the new topics that we cover today will be resilience, toughness and impact testing, hardness testing and hardness. And then we will change topics. This is all testing and so on. We will change topics to plastic deformation of polycrystalline metals. And inside that, we will cover several topics, and the first of that will be effect of grain boundaries on strength. So this is what we will cover today. Let us quickly remind ourselves about what we did in lecture 3. Last time was a quiz, so lecture 3 may not be very fresh in your minds. We continued with the yield strength discussion, and we talked of the 0.2% yield strength and how to find it. We discussed yield strengths of different materials, categories of materials. Then we defined the ultimate tensile strength and talked of necking and what happens. Gave you examples of necking and failure, and for an annealed material and for the same material in a tempered condition when it is higher strength. We showed you the whole change in the material as it goes through the tensile test, especially the necking after ultimate yield strength and the ultimate fracture. We compared tensile strengths of different categories of materials. We then defined ductility first as percent elongation, and we showed you the blue one has a smaller percent elongation, the green one has larger percent elongation, and so on. And then we defined ductility as percent reduction in area. We solved a simple problem about ductility. It was not something big, but of course remember that the area when it is round is either pi r squared or pi by 4 d squared. So you can find the same cross-sectional area in terms of the radius or in terms of the diameter. Then we compared a lot of different metals, magnesium, nickels, steels and other things in terms of their strength, which is the vertical side, the height of the curve, and in terms of ductility, which is horizontal side, right? So any curve horizontally, if it is big, then the ductility is high. Any curve which is high, then the strength is high. And some curves, both strength and ductility are good. Some curves, both strength and ductility are low, but there are lots of varieties. Then we started talking about the true stress and the true strain. We defined that it is now the force divided by the current area, the instantaneous area AI, rather than the original area A naught. And we defined that the strain is also same thing, dl upon L, change of length, right? Change upon length, integral, and because it is 1 upon L dl, so this becomes ln L I upon L naught. This can also be written as ln of A naught upon AI, and this is possible because the volume remains constant. Initial volume L naught into A naught is equal to instantaneous or final volume Li into AI. Therefore, L naught upon Li is equal to this and that, right? So we defined true stress and we defined true strain and how to calculate them. We showed you the difference of two materials. This is a low carbon steel, for which the black one is the engineering stress strain curve, and the pink one, or whatever you call it, is the true stress strain curve. We showed you the same thing in a different way, the true stress and the engineering stress curves, but then we divided them into two big areas of elastic and plastic region, and the plastic region we divided into yield region, strain hardening region and necking region, and we explained in detail the reason why they are named like yield and strain hardening and necking. Then we did a problem on true stress and true strain. The values are given. You solved it yourself hopefully, and then I solved it for you. So this was the solution. We found the initial area, the final area, we found the true stress the engineering stress, right? And then by using the true strain formula of Li upon L naught, but then that Li upon L naught is also A naught upon Ai, so therefore we calculated it and so forth. So that was the previous lecture. So now let us start. We will continue. I will remind you that this is the stress strain curve, the full stress strain curve that you get after the tensile test. And we have covered the slope here, the slope, the elastic modulus, end of the straight line, the yield strength, maximum point, the ultimate strength, fracture point at which the strain is the ductility of the material, and then true stress and true strain. But there are one or two more properties, extended properties. These four are the four basic ones: elastic modulus, yield strength, ultimate strength, and ductility. But there are one or two more which we will just show you. So just read the heading, resilience. Don't read anything else, like I always request you. Now tell me in English language, forget about material science, forget about engineering. In English language, you have done lots of courses in the foundation. What is resilience? When you say that this man is resilient, then what do you mean? So those of you who remember, if you put a pressure on somebody, some friends are trying to make somebody go into bad habits. He was not having cigarette and so on, but some friends said, have cigarette, it is very nice. If he resists and he does not do it, then he has more resilience. But if he agrees, then resilience is not there, right? So resilience is a sort of resistance to deformation. So it is not a strength. Strength is resistance to deformation. But here now let me show you. Resilience can be defined as the ability of a material to store energy in the elastic region. Do you understand? You see, in the elastic region, that is for a metals, it is the linear part of the curve, the straight line part of the curve. So as long as you are in the straight line part of the curve, you are trying to work on the material, isn't it? You are working on the material, so it is deforming. Of course, it is elastic, so when you remove the force, then the material goes back to zero deformation. You can increase it, the load and so on, until you reach the yield point. So as long as you are just below the yield point, so the load is very high, there is quite some deformation, but as soon as you remove it, all the deformation is gone, right? So work and energy are the same thing. When I apply work, when I force on the metal, when I apply work, then inside the material the energy changes. The stored internal energy of the material changes. So because of that change in the energy level of the material starts to move and deform. But because it was elastic, so all that extra energy that we stored inside will go away. Once it will become plastic, some energy will permanently be there. So the amount of work that we can do on the material, as long as it is elastic, the last point just before the yield point, that much work or that much energy, that is known as resilience, right? So we can say that it is the work done on a material in the elastic region, or it is the ability of the material to store energy in the elastic region. So if the symbol is U sub R, resilience, this is called resilience, then you see this is the straight line region. So if this is the yield point, then sigma y is the stress and some strain epsilon y, right? Some strain, that this is the point which is the end of the yield, elastic region. So if this is the yield point, in some other materials it could be straight line. It could be, we are deliberately showing you where you have to do the 0.2% yield, but this is now the yield point. So find the stress at the yield point, find the strain at the yield point. So this is just that. This is the stress sigma d epsilon integral. So if you integrate it, you will get stress into strain from 0 to epsilon y, right? Stress into strain. So actually you are just multiplying, because at 0 everything is 0. At this point the stress is sigma y and the strain is epsilon y. So this thing is called the resilience of the material. Resilience of the material. Now suppose this is a straight line. That I am showing a slight curve, but suppose this is the straight line. So if this is a complete straight line, then this vertical side is sigma y, this horizontal side is epsilon y, and it is a triangle. And what is the area of a triangle? Yes, you are very right, half base into height. So half base into height. So half epsilon y into sigma y. This is the area of the curve. So if it is a slight curve, then you do the integral, you do the sigma d epsilon integral from 0 to epsilon y. But if it is a straight line region, then it is simply half sigma y into epsilon y. So this area under the curve in the elastic region, right? It is very critical. The area under the stress strain curve in the elastic region. This is called the resilience of the material. This is called the resilience of the material. That how much work do we need to do on the material so that it reaches the end of the elastic region, or how much energy is stored inside the material when we load it until the end of the elastic region. This is called the resilience. Okay. Now toughness. Don't read. We have already told you toughness earlier. We have talked about it a little and so on, but we will talk about toughness more. So if you look at the graphs now, the pictures, you see there is this material, blue, and there is area under the curve. There is this green one, area under the curve. There is this pink one or purple one, and area under the curve. This time we are not taking the area under the curve only in the elastic region. Otherwise we will take area only until here, or we will take area only until here. We are taking the area under the full stress strain curve. So the amount of work that we need to fracture the material, right? Because the full stress strain curve means what? That at this point it fractures, at this point this fractures, at this point this fractures. There are three different types of materials. So the amount of work that we need to do on a material to fracture it, this is the toughness of the material. And in other words, the ability of the material to store energy until fracture. This is the toughness of the material. And calculation wise, this is the area under the full stress strain curve. So if you compare to previous, resilience is also toughness, but resilience is the elastic toughness, right? Resilience is the toughness in the elastic region, and toughness, just toughness, is the toughness of the full curve until fracture. So this is the resistance of the material, but this is an energy now, right? They say stored energy, amount of work, stored energy and amount of work, right? So if the material is brittle, it will have only elastic energy, there will be almost no plastic deformation. But if the material is ductile, there will be the elastic plus the plastic region. So if this is green is the material, if I draw a straight line here and take the area, then this is the resilience. And from here to here, it is the remaining one. So that resilience is the energy of the elastic region, the rest is the plastic region. If I add them, then the complete is called the toughness of the material. Okay.